Good morning, everyone. My name is Arnav Kumar from the Reaxys product team, and I'm here with my friend Moritz and collaborator Moritz from ETH Zurich. Today, we'll talk about Reaxys Predictive Retrosynthesis, its development, use, and adoption by chemists. Very briefly, I'll touch upon how the Reaxys Predictive Retrosynthesis tool was developed. Moritz will talk about its use and adoption by chemists in his research group, and we'll briefly look at the future roadmap. Small molecule discovery essentially needs to answer two questions. First, what to make, and second, important question is how to make it. And this is where we are focused on synthesis planning. Researchers and chemists spend a lot of time doing synthesis planning. So we ask the question, can data-driven approaches improve synthesis planning? This idea is not new. It has been around since the time of E.J. Corey, who won the Nobel Prize for having computer-aided synthesis planning. The critical requirements for any predictive retrosynthesis tool is one, it delivers scientifically robust predictions so that chemists can trust it. And second, it is user-friendly and intuitive so that chemists do not require to spend a lot of time in learning how to use the tool. The key elements for success of any predictive tool, not only retrosynthesis, but any predictive tool there are three key elements. One, the data science needs to be top-notch, i.e. the algorithm needs to be really good. This algorithm needs to be married with high-quality data to give robust outcome, to predict robust outcome, scientifically robust outcome. And third, that it should be delivered to users in a very user-friendly manner so that they can get on with it very quickly. Let's discuss algorithms and data. The success of predictive retrosynthesis models depend on both algorithm and quality of data that these algorithms are trained on. We believe that Reaxys reaction data offers the best data for predictive modeling. This is evident by the number of research groups and corporate organizations who use Reaxys reactions data to drive build new predictive models. Similar to the academic groups that have used Reaxys reactions data, we collaborated with Mark when he was at University of Münster. And Mark wrote one of the most cited works in the field of predictive retrosynthesis. His approach was a game changer because for the first time, deep neural networks and Monte Carlo tree search were applied to solve the problem of retrosynthesis. Through the application of these innovative technologies, the tool has learned to transform chemistry rules from Reaxys reactions data, has learned to prioritize those rules, and uses efficient search method to prevent combinatorial explosion. The tool is trained on 15 million unique single-step reactions from Reaxys, from which roughly 400,000 reaction rules are derived. These are used to train the neural network and combined with Monte Carlo tree search. Through the unique combination of this technology and data, we are able to deliver fast, robust, and innovative route prediction. Now let's discuss design and ease of use. Reaxys Predictive Retrosynthesis is fully integrated in Reaxys. Users are able to view published and predicted route in a single view. Commercially available starting materials needed for synthesis can be easily ordered using the shopping cart feature. The number of steps required in a synthesis route for easy comparison are provided. And a route topology is given to quickly assess the linearity or branching or complexity of the root. Further to this, in detailed tree view, the root topology is provided on the top for easily toggling between roots. Literature references of published roots that inform predicted roots, including the experimental procedures, are provided so users can make informed decision about whether this transformation will work. And secondly, what potential experimental conditions they can use to carry out such transformation. We have newly introduced the ability to extend root by adding one reaction step at a time. These reaction steps could be published or predicted, so users have more control now. And when you're happy with the root, these can be exported in multiple different formats for sharing or adding to electronic lab notebooks. We think we have built a predictive retrosynthesis solution on these three pillars, and we think it's a good solution. Let's now see how it performs in the hands of chemists. Over to you, Moritz.
Thank you very much. Yes, when we got first approached by Reaxys, we were delighted to be given the opportunity to work on such new groundbreaking technology as AI-driven or generally predictive synthesis starts to get bigger and bigger. We obviously were happy to be involved there. And so in order to get the most out of it and to find out the best data set for this program, we went out and divided our group into 7 teams consisting to 3 to 4 researchers each, and they were made up of senior and junior students within our group. So we have a large variety of different experiences within those smaller groups. These groups then selected 30 molecules from a variety of different fields, get a large structural diversity here. So as you can see down at the examples of some of the molecules chosen, we have very drug-like molecules, but we have also molecules that might very well be natural products or at least intermediates towards the synthesis of a very complex natural product. Groups then got assigned a couple of those molecules, and within the group came up with the first routes without using the predictive retrosynthesis tool. These routes were then carried towards other groups and were assessed for their scientific viability, while also factoring in how much time and effort was required in order to get to a synthesis which we were comfortable with. Next, we then moved towards implementing retrosynthesis prediction into our routes and fed the molecules into the tool. At this point then, these routes were taken up by the groups and again compared with our generated routes, and also checked for their viability to find out which steps are likely to work and which steps may be problematic. Since the tool, however, keeps developing throughout the time that we used it, we sometimes went back a couple of times and actually fed a couple molecules, not all of them, into the tool again when new features were added in order to find out how these features improve upon the workflow which we can have for these molecules. So in order to see how the group actually rated the tool and how they worked with it, we want to quickly show the results of an internal survey we did. People had to answer a couple of questions. We can see that it was rated very highly on how intuitive it is to use and how user-friendly the interface is. Generally, the people here seem to be in agreement that, for people who are familiar with Reaxys, they can translate that knowledge very well to this tool. Next, people were also very fond of the ability to review reaction conditions and literature references for predicted and published steps. The integration here was generally seen as very positive as well. A more mixed picture we see for the question of if the generation of new ideas is facilitated by the tool. And we see here that some people are very happy with it, while some people are not that happy, which we most likely attribute that to the fact that drug-like molecules are very well supported by the program, while more complex molecules often pose a bit of a challenge to the program and seems to stutter there from time to time. So without further ado, let's now move on to a couple of examples of routes here. First, I want to start with a more drug-like molecule, which looks rather similar to molecules that can be found in the development process of pharmaceutical companies. So firstly, we see the human-generated route, which chooses a available cheap starting material from catalog retailer Sigma Aldrich, and then builds up linearly to the final product. The key step here being most likely the double reductive amination in order to form the bridged sort of pyridine ring. Moving on to our retrosynthesis tool route, we see that the approach actually is quite a bit different. There's not a more linear route chosen, but actually a convergent approach, bringing two fragments together in a last step in order to form the product. And again, we see that the step here is also formed, ring here is also formed through the formation of an iminium, which then does sort of a Spengler reaction in order to fuse it to the imidazole ring. So as a takeaway for this, we can say that both routes are interesting and robust routes, both by our group, but also by the retrosynthesis tool. And we can say the conditions shown here are generally, especially for the retrosynthesis tool, are extracted by the groups who have worked on those molecules from the retrosynthesis tool. As always, multiple conditions are given by the tool. This again shows how easy it was for the groups to obtain quite good conditions for these transformations in which they had high belief that they will work. But furthermore, we can see that the tool and our approach differ in one key factor, and that is the choosing of starting materials. While we went back and went for more the catalog approach in order to find chemicals which we can easily access, the tool actually went to more complex starting materials, which can either be prepared over a couple of steps or potentially in an industrial setting, for example, be outsourced to a contract synthesis company. So we kind of already see here that the tool can provide insight in maybe very complex starting materials which are still available. Moving on to our second drug-like molecule, this was a molecule that was part of a bigger peptide project and was synthesized in our group. So we can see here the approach of our group is relatively straightforward. Key to the synthesis most likely being the Michael addition of the ethiolate into an innovat and trapping of the resulting enolate with decanal in order to rapidly construct the carbon skeleton here. Looking at the retrosynthesis tool route, we see a quite different approach. The starting material is still widely available in just cysteine, which is then transformed to the thioether. So here, actually, the first bond to form the 7-membered ring is the thioether, not the amide bond. We then see to close the 7-membered ring an amide bond formation, where we can see that the program might have a small hiccup here. As we can see, it tries to form an acid chloride in the presence of later aqueous HCl. This might not be most feasible step, however, can be easily be avoided by changing the order of steps and having the debug protection in the first place. So we can clearly see that both routes here are robust, but the input of chemists is still very much needed in order to teach the tool some things that it might not know inherently, like some functional proof stabilities or how they just perform in certain steps. But again, I would say a very, very solid route that was developed here. So if we move on and now look more at like natural product-like molecules, which are clearly a little bit more complex, we want to have examples of that as well. So looking at this is a molecule that was at n part of a synthesis in our group and a fragment of a larger molecule. And we can see here that this decalin system is built up pretty rapidly in our route by a Konya-ene reaction, and then later through sort of reductive amination and coupling the carbamate is formed. Looking at the predicted route here from the retrosynthesis tool, we see an approach that, while sharing some similarities, actually is still a bit different. So through hydrocirculation and 1,4 addition, we form the precursor, which then under Claisen conditions closes the decalin here. However, it has to be noted, late game of the synthesis from the tool looked again very solid. One point that has to be highlighted though is the Wittig olefination of the diketone. It looks like this might be potentially a feasible reaction, as this ketone is most likely the more accessible of the two, but this is not completely safe. However, having the integration here of the retrosynthesis tool into Reaxys and so being able to quickly look this up through a Reaxys search, this can actually be verified or found out to be a problematic step, and then in order to potentially be replaced by a different step. So the integration here is a very important takeaway in order for chemists to have a deep dive into certain steps where they might not be completely sure whether they will work as predicted. Moving on to the final molecule, which again, it's sort of a derivative of a molecule that has been made in our group before, and was chosen very deliberately. Because looking at this molecule, it has a very, for us, very clear disconnection within it. This is a nitrile oxide cycloaddition. So looking at this molecule, our route basically focused on that immediately, just as quickly as possible, generating the precursor for that, and then finishing up the synthesis of this molecule by nitrile oxide cycloaddition. We were kind of interested how the program would handle this, and to our surprise, we can say the program did not want to do a nitrile oxide cycloaddition, but do something completely different. In that case, it's an oxidative cyclization, which I have to state I wasn't aware of before the program told me that this is an option to do here. So this was very, very interesting, because here this clearly we were very set out in order to find just the one route which we could think of, and the program actually provided something different. But, and if we look at the initial route, we see that now the program actually has a lot of problems. So the transformations shown here are as predicted by the program, and these are clearly not feasible. However, as a new feature has been added after some time working with the program, which is going through guided routes and actually doing it step by step through the tree search, we were actually able to guide the program towards a route which we think is pretty solid towards the cyclization precursor, and then could lead to implementation of this innovative step. So I would say this is actually pretty cool that this program sort of can eliminate a bias here that we might have had for this molecule, and actually give us something new here. And then even if it has problems at a point, we can actually use the ability to custom build a route, guide it towards a route which we are more comfortable with and think can potentially succeed. So what is the takeaway for working with this molecule, with this tool for us? What we can definitely say, the tool is very, very user-friendly. It is easy to use, and if you're used to Reaxys, you can very well translate your knowledge there to this tool. The routes it comes up with are also pretty robust, especially for drug-like molecules. However, they might still need some review at some points for steps which are not completely clear whether they will work. However, as the tool is very well integrated in Reaxys, reviewing these steps is very easy and brings us to our next point, that it saves a lot of time by having everything in one place. So being able to design a route, customize it, look up the literature in one place makes this very, very time-effective way of planning a synthesis. It has also to be stated that, as we saw in the last example here, these connections are pretty innovative at some point and can actually help to eliminate a bit of bias that we potentially in synthesis can experience at one point, because we're just so focused on one particular disconnection. So this is very, very cool, even for more complex molecules. These, however, are also the challenges. It's clearly for complex natural product that the program has a lot of issues, can often not provide a full route. However, with its sometimes very cool disconnection and guidance, it can actually be made to form pretty robust routes for these molecules as well. So where does this bring us? It brings us to the point that this tool is the perfect tool for a chemist to apply his knowledge or her knowledge on a synthesis. So this tool is not made to replace a chemist. It's very much a tool that adds to our toolbox and to our workflow when we want to create a synthesis plan for a molecule, as we can basically use this in order to apply our knowledge and get more and more information out to make such molecule. So I think this was a very important takeaway for us. This program is a lot of help to us, and it's very, very good for our workflow, but really also still needs our input in order to provide very, very nice routes. So this interaction between those two sides is very important. And we can see this with the feedback that the group gave. A lot of people were quite happy about how the program made them able to access literatures, about the disconnections that they wouldn't have thought of, and especially also how much time it saved for these like drug-like molecules where the provided syntheses are very, very good to start with. So, however, working in this collaboration is also fantastic because we can actually give feedback for things where we think there is more that can potentially be added. And this is so great about it. We're users here, but we can really give input as well. And there are some things which we would like to see in the future potentially to be added. A lot of people were quite in favor to get even more potential to guide this tool, having options to protect certain bonds or to clearly state, I want you to break this bond in order to help the tool even more for these more complex molecules, for example. Some people wanted to have be able to define certain intermediates or starting materials. This might be interesting. For example, if somebody wants to do a molecule starting from chiral pool, where there's just a limited amount of molecules available. And last but not least, it is also a wish from a lot of people that they are able to exclude certain steps from the predicted synthesis. These might be to the fact that we're not able to run those reactions if there are very specific reactions where we are lacking the equipment to do the reactions. Also, it might potentially be because we believe that this step, the tool predicted at that point, cannot work in the setting. So being able to exclude that step might help us also to develop more complex routes for complex targets, which we really believe in. With that being said, it was a pleasure for me talking about this, and I want to give it back for the future of this program to Abhinav.
Thank you, Moritz, for that tour de force. And with that, let me just show you. So, besides working with Moritz and ET at Zurich, we also work with a lot of pharma and agrochemical companies, and predominantly the feedback that we receive really align well with what you have heard from Moritz. So the tool that we have built is user-friendly and very user-friendly. It does provide innovative disconnections and helps with and saves time with synthesis planning. And really the routes proposed for especially drug-like molecules are mostly robust. We are constantly developing the tool further, and feedback, we are, our roadmap of development is user-centric and guided by chemist feedback. So we are very, in a way, very thankful to Moritz and Professor Carrera's group for providing valuable feedback. As you heard from Moritz, so, chemists want more control. So that's what we are working on. So to give, our roadmap is divided into 3 parts. Giving chemists more control. So to be able to define bonds to break, to be able to define intermediates to be included or excluded. Second, to improve and augment the predictive model even more. What this means is that, firstly, we update the model with the latest Reaxys data, because every half a year, you have a lot of new chemistry being published. Every quarter, there's new chemistry being published. Second, to improve the diversity and of the routes that are proposed, as well as improve the respecting of functional groups, as Moritz was alluding to earlier, and regioselectivity. And importantly, what we also are working on is to give the ability to customize the model by including or by training the algorithm on combined Reaxys and customer reactions data. Because a number of companies, some academic groups use electronic lab notebooks, and there's a lot of reactions data sitting in there, which will be, which can be combined to make the algorithm more stronger. Lastly, we are working on improving the ability to edit synthesis plans even more. So giving the users the ability to delete steps that they do not like, delete routes or projects that they do not, delete routes that they do not like. And importantly, which would be delightful for all the chemists, that to be able to export it as the retrosynthesis tree as a ChemDraw file. So that, it makes the sharing even easier. With that, I would like to, I hope we have been able to show that the tool is built on these 3 pillars and really augments chemist knowledge and helps accelerate synthesis planning by providing robust route suggestions. I would like to thank my collaborators at ETH Zurich, Moritz and Professor Carrera's group, and also the whole Reaxys team. So it has been a great working experience with Moritz, and we continue working. It's not, our collaboration runs further.
Thank you, back to you as well. It is a pleasure. It's truly fantastic to work with such a great team on such a great field that is developing that rapidly, and being able to have that insight into this, and also learning on how to use it for our own workflow has been fantastic.
Thank you very much, everyone, for listening to us.
Thank you.